In this section, we are going to look at an application of implicit differentiation called related rates. A related rates problem typically gives us one of the rates of change at a given point in time, and we want to find the other rate at that exact instant. So we need to find an equation that relates the rate we're looking for to a rate that we already know. Here are some general guidelines to answering related rates questions. 1. Read the question carefully, draw a picture or diagram if possible. 2. Organize what is being asked for and what is given. Define variables for quantities that are changing with meaningful letters of your choice. Identify the goal of what you are asked to find. 3. Use your previous mathematical knowledge from algebra, geometry, trigonometry, etc. to write a relationship or equation between the variables that are changing. Sometimes this step involves more than one equation. 4. Use implicit differentiation to differentiate both sides of the equation with respect to the independent variable. This is usually time, but not always. Now you have an equation that describes the relationships between rates of change of different quantities. If a quantity is decreasing or getting smaller, it should be negative. 5. Substitute the given information into this equation and solve for the unknown rate of change, your goal. Example 1 says write the derivative notation that represents the rate of change described in the examples below. Part A, we have the rate of change in distance over time, and we're given the variables, so the derivative notation would be ds over dt. B, change in volume of a balloon as the radius r of the balloon changes. So in this equation, or in this instance, our rate of change would be dv dr. C, change in volume of a balloon as it's blown up. Notice that we don't know what the independent variable, or it's not explicitly stated, but as it's blown up means over time, so it would be dv over dt. D, rate in which the angle of elevation theta changes as the plane speeds up, so its velocity. So we'd have d theta over dv. And then E, how fast is the angle of depression theta decreases as we get closer to sunset. As we get closer to sunset means more time is passing, and so for this one, we would have d theta over dt. All right. Example 2 says, suppose there is an oil spill from a ruptured tanker and it spreads in a circular pattern in the ocean. If the radius of the spill is increasing at a rate of 1 meter per second, how fast is the area increasing when the radius is 30 centimeters? All right, let's draw a picture of what is being described here. So a tanker is a type of boat, and it carries oil here, or other types of things. And so let's say that we are in the ocean, and pretend we have an aerial view. So we're looking from up above, and let's say here's our boat, and it's leaking oil into the ocean, and it says it's happening in a circular pattern. Let me try again and draw a better circle. All right, so here's my circle that represents the oil spill. And remember, the oil spill is getting bigger. And so this is just thinking of it like a picture or a moment in time. So maybe you can think about it like having a drone, and you're flying over the ocean with your drone, and your drone happens to snap a picture at that one instant in time. But essentially, we have a couple of things. So we talked about the first step being drawing our diagram. And then the next thing that we could do is organize what is being asked of us. So I want to define a few variables. It says how fast is the area, and so because we're talking about a circle, we can define that later, but capital A, I want this to represent the area of the circular oil spill. And the other thing that we have is the radius of the circular oil spill. All right, so we've defined some variables, the area and the radius of our circular oil spill. Now what I'd like to do is I'd like to define my goal. And so my goal is to find how fast is the area increasing when the radius is 30 centimeters? So the area is increasing over time. So the rate that we're trying to find is dA dt. So that's our goal. That's what we'd like to try to find here. Okay. Now, what we'd like to do is step 3 says use your previous mathematical knowledge from algebra, geometry, trigonometry, etc. to write a relationship, which is another word for write out an equation between the variables that are changing. So another helpful tip that we could do is kind of try to identify what kind of related rates problem this is. So I'm going to come over here and say that this is a circular area related rates problem. And we'll define other ones or other types of related rates problems later on in this video. So because this is a circular area, I'd like to create my equation to relate the area and the radius of a circle, which if you don't remember, the area of a circle is equal to pi times the radius squared. Now, because we are trying to find dA dt, that means we have dt here, so what we're doing is we're taking the derivative of this equation with respect to t on both sides of our equation. So I'm going to take the derivative with respect to t on the left-hand side of my equation, and then the derivative with respect to t on the right-hand side of my equation. And so if we use chain rule and we use implicit differentiation, on the left-hand side we will get dA dt is equal to pi. I can factor out since that is a constant, and then I can multiply this by the derivative with respect to r of r squared times dr dt, and the derivative of r squared, that is going to be 2r. So let's rewrite this. We have dA dt is equal to pi times 2r times dr dt. Okay, so again, we're trying to find the rate of change of the area specifically when the radius is 30 centimeters. Now, think about this. Again, I'm thinking about a drone. I've snapped a picture, and this is an exact moment in time. And so the rate at which the area is changing is going to be different at different times. But in this particular moment, it's asking us when the radius is 30 centimeters. So let's plug that into our equation. Again, our goal is to isolate or find dA dt. That means that for all of our other unknown values, we should be able to plug them in with numerical values. So dA dt is equal to pi times 2 times our radius, which is 30 centimeters. And then dr dt represents the rate of change of our radius, which it says that the radius of the spill is increasing at a rate of 1 meter per second. So I'm going to put 1 meter per second. Now, you might notice that we're going to run into an issue because our units are not matching up. So notice that here this is centimeters and this is meters, and we need those to be in the same units. So I'm going to convert 30 centimeters. That is the same thing as 0.3 meters. Now we are cooking. So if I multiply the units together, that's going to give me meters squared per second, that's what we would expect for the rate of change of area, because area is measured in square units. So now we have dA dt is equal to 2 times 0.3 is 0.6 pi, and then multiplying by 1 just gives us that, and our units are meters squared per second. All right, so it's really important that we are able to interpret what our answer is saying. So I wrote a sentence here that says, when the radius is 30 centimeters, the area of the oil spill is increasing at a rate of about, and then I plug this into my calculator, and 0.6 times pi is about 1.8850 meters squared per second. So there is the interpretation of our answer. Let's go over some more examples. Example 3 says, a passenger ship and an oil tanker left port sometime in the morning. The former headed due north and the latter headed due east. At noon, the passenger ship was 40 miles from port and sailing at 30 miles per hour, while the oil tanker was 30 miles from port and sailing at 20 miles per hour. How fast was the distance between the two ships changing at that time? So, step one is, if we can, let's draw a diagram. So here, I'm going to have this dot represent the port. And remember, in this picture, I'm going to pretend I have a drone and I'm going to do an aerial view. So I'm looking from above, and it says that the passenger ship headed due north. And so if we think about the port like our origin, then due north means that we're heading in the direction of the positive y-axis. So something like this. And then I'll put a dot here to represent my passenger ship. And I'm just going to put PS for passenger ship. And then the oil tanker, it says headed due east. So again, if we think about the port like our origin, that means we're traveling along the positive x-axis. And so I'm going to put a dot here and put OT for oil tanker. At noon, the passenger ship was 40 miles from port and sailing at 30 miles per hour, while the oil tanker was 30 miles from port and sailing at 20 miles per hour. How fast was the distance between the two ships changing at that time? So now what I'd like to do is I'd like to define some variables. I'm going to define x to be the distance between the port and the oil tanker. So in my picture, it would be this horizontal distance here. That would represent x. And I'm going to have y, I'm going to define this variable to be the distance between the port and the passenger ship. So in my diagram, I'm going to label this as my y value. It's the vertical distance here between the passenger ship and my port. The other thing that I can do now is, in my diagram, I can connect my passenger ship and my oil tanker with a straight line, and I want to define another variable. I'm going to call it c, and I'm going to have c represent the distance between the passenger ship and the oil tanker. All right, so I've created a bunch of variables. Now what I can do is I can define my goal. My goal is to find how fast was the distance between the two ships changing at that time. So we define the distance between the two ships to be c, so our goal is to find dc dt, the rate at which the distance between the ships is changing over time. And another thing is, if we want to identify what kind of related rates question this is, looking at our diagram, we have a right triangle and we're trying to relate our three variables, x, y, and c, and so you might recognize that this is going to be a Pythagorean theorem question. Okay, so if this is a Pythagorean theorem question, let's create an equation that's going to relate all three of our variables, and that equation is going to be x squared plus y squared is equal to c squared. From here, I can take the derivative of both sides with respect to t, and I'm going to use implicit differentiation. Okay, so if I take the derivative of both sides, let's see, I can separate the left-hand side because we know the derivative property that the derivative of a sum is the sum of the derivatives. On the right-hand side, I'm going to use chain rule, and then I would need to multiply this by dc dt. I need to also use chain rule on the left-hand side. And I can take the derivative of c squared, which would be 2c. All right, so let's start taking the derivative on the left-hand side of our equation. So I'm going to get 2x times dx dt plus 2y times dy dt is equal to 2c times dc dt. Now notice every single term on both the left-hand side and the right-hand side all have a 2 or a multiple of 2, and so I can actually divide both sides of my equation by 2, and so if I do that, then we end up with this new equation. And I just want to emphasize that our goal is to find dc dt. So I'm going to box this here. dc dt is what we are trying to find. That means that for every other unknown value, we should be able to come up or substitute in some numerical value so that we can get a final answer for dc dt. So let's think about what these numerical values are going to be for each of these unknowns. All right, so let's look back at the given information. It says at noon, the passenger ship was 40 miles from port and sailing at 30 miles per hour. So what we're doing is this picture or this diagram that I've drawn, this is specifically at noon or at 12 p.m. So we've frozen this instance in time because we took a snapshot picture. Normally, the passenger ship and the oil tanker are moving, but at this one instance where I've snapped my picture, I can figure out these distances that they've traveled. So at noon, the passenger ship was 40 miles from port, meaning that in this picture, this represents 40 miles right here. And it's traveling at 30 miles per hour, while the oil tanker was 30 miles from port, meaning that this distance here is 30 miles. Okay, so let's figure out in our equation what these things are then. So our x value represents the distance between the port and the oil tanker. And if we're thinking about this, again, specifically at noon, at this exact moment in time, then our x value was 30. And why don't I put units to see that our units are going to end up working out? So my x value, the distance was 30 miles. Now I want to figure out what dx dt is. And dx dt is going to represent the rate of change between over time of the distance between the port and the oil tanker. And so that's another way of saying what is the speed of the oil tanker. And it says here that the oil tanker was traveling at 20 miles per hour. That was for the oil tanker, which is like the horizontal distance. So I'm going to fill that in here. I have 20 miles per hour. Now I'd like to find the y value. And the y value, it says the distance between the port and the passenger ship. So that's what y represents. And at noon, we see that that vertical distance was 40 miles. And then we want to multiply this by dy dt, which represents the rate of change over time of the vertical distance. In other words, that's the speed of the passenger ship, which it says is sailing at 30 miles per hour. So I'm going to put 30 miles per hour here, and this is equal to. Now, in this snapshot moment, we want to figure out c, which represents the distance between the passenger ship and the oil tanker. And in this picture, we don't actually have c, or the numerical value for c, at noon at that exact moment in time. However, we can solve for it using the Pythagorean theorem. So the relationship is that c squared is equal to 30 squared plus 40 squared. If I take the square root of both sides, and if you solve this, this ends up being 50. This is actually an example of a Pythagorean triple. If you don't know what that is, feel free to look it up, but a Pythagorean triple is essentially three numbers, or three integers specifically, that satisfy the Pythagorean theorem. And so 30, 40, and 50 are all integers. All right, so we use that to find c, which was 50 miles, since c is a distance. And then we're multiplying this by dc over dt, which is what we would like to try to solve for by isolating that. Okay, so now what I'd like to do is I'd like to divide both sides by 50 miles, and that's going to get rid of that. And then here I'm going to divide this by 50 miles. And notice that the 30 miles and the 40 miles, I could factor out the miles and then divide it with the miles in the denominator. So my final units are going to end up being in miles per hour, which makes sense given what we are doing. So I'm going to clean this up a bit. All right, so if you end up simplifying this fraction, you end up getting dc dt is equal to 36. And then notice that the units that would be remaining are, we have miles per hour plus miles per hour, so our final units would be in miles per hour. So I'm going to go ahead and write up an interpretation for what this means. All right, so what we have is, at noon, the distance between the oil tanker and the passenger ship was increasing at a rate of 36 miles per hour. And some things that I'm looking for are the units. So you want to make sure you include units, so it's not 36 minutes or 36 donkeys or apples, it's miles per hour. And then the other thing that I really want to emphasize is it was at this exact moment in time, because at 1 p.m., the rate of change of the distance is going to be completely something else. And so this changes, which is why we like to think about this as you're taking a snapshot moment in time. You're taking a picture and you're freezing it in that exact moment at noon is when the related rate or the distance between these two ships is changing or increasing at a rate of 36 miles per hour. Let's go ahead and look at another example. Example 4 says, a boat is pulled into a dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 1 meter higher than the bow of the boat. If the rope is pulled in at a rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? Round your final answer to 4 decimal places. So as always, as we're getting started out with these related rates questions, if possible, I'm going to try to draw a diagram. All right, so I've drawn my diagram to include the dock, the boat, and this pulley system, and in the pink is what we have as our rope. So let's go ahead and, based off this, define a few variables for the quantities that are changing. So I'm going to define x to be the distance between the dock and boat. And so in my diagram, that would be this distance here, that is going to be x. Now, maybe let's not use y. Y I usually reserve for vertical distance. Let's call it c. I'm going to let c represent the length of the remaining rope. And so in my picture, c is this pink thing here, that length or distance, whatever you want to think about it as. Okay, so something you might notice is that this thing here is a right angle, and so likely this will be a Pythagorean theorem question since we have a right triangle. But let's check it out. Also, I want to say, sometimes students are inclined to say, why don't we let y equal the length of the pulley? And in fact, maybe I'll put vertical length even. You can still get the same answer this way, but what's going to end up happening is when you take a derivative and you get to dy dt is 0, and so you'll still end up getting the same answer, but it's more work. And the reason that I'm not giving the vertical length of the pulley a variable is because a variable is something that changes quantity, the thing that we're measuring. But in this case, the height of the pulley is not changing. This 1 meter, the height of the pulley, is constant. And so that's why we're not giving it a variable name. And so it's actually going to end up working out easier if we think about it because it is a constant. So if we're thinking about the Pythagorean theorem, then the equation we want to use is x squared plus 1 squared is equal to c squared. Let's also define our goal. What is our goal? We would like to find if the rope is pulled in at a rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? So how fast is the boat approaching the dock? And that is related to this thing, the distance between the boat and the dock. How fast is that changing? And so the thing that we're trying to find is dx dt. All right, let's go ahead and take now the derivative with respect to time of both sides of this equation. Okay, so I'm going to take the derivative with respect to x. So let's use chain rule. Times dx dt. And then if I were to take the derivative with respect to t of 1 squared, that's a constant, so that's going to end up being 0. And then I have the derivative with respect to c of c squared times dc dt. So if I take the derivative, I get 2x times dx dt plus 0. The derivative of 1 is going to be 0. Then we have 2c times dc dt. Once again, I'm going to erase the 0 here. I can divide both sides of this equation by 2 because both sides are being multiplied by 2. And if I did that, I would end up with x times dx over dt is equal to c times dc over dt. So let's figure out what some of these values are. It says in the exact moment in time that we're snapping our picture and freezing, it says when it is 8 meters from the dock. And so here we've snapped our picture when this is 8 meters. And we also want to figure out c, and let's do that by using the Pythagorean theorem. So c squared in that exact moment in time is equal to 8 squared plus 1 squared. And if I solve for c, we end up getting the square root of 65. So okay, I'm going to erase this, and let's plug in some values. And remember, eyes on the prize, so our goal, we're trying to find dx dt. That means that I should be able to come up with a numerical value for every other unknown. So x at that moment is 8. And why don't I put units and practice good habits? So it'd be 8 meters times dx dt is equal to the square root of 65 meters. I'm running out of space. And then I want to multiply this by dc dt. So let's take a moment to think about. It says the rope is pulled in at a rate of 1 meter per second. Now we want to be careful because c represents the length of the remaining rope, and that value for c over time is getting smaller. And if you remember from our checklist or our laundry list from earlier, it says if a rate of change or if something that we're measuring or a quantity is decreasing, that means that the rate of change is a negative number. So I'm going to put here that it's negative 1 meter per second. Okay. So now what I'd like to do is I'd like to divide both sides by 8 meters. And notice that these meters will cancel out, and so our final units are going to be in meters per second, which is something that we would expect since we're finding dx dt, and that is the rate at which the boat is moving in closer to the dock. Okay, so dx dt is equal to negative square root of 65 over 8, and then our units are meters per second. Let's go ahead and write a sentence to interpret what this means. All right, so the interpretation of our answer is, when the boat is 8 meters from the dock, the distance between the boat and the dock is decreasing at a rate of 1.0078 meters per second, and it asks us to round our answer to 4 decimal places, which is what I did. I threw that into my calculator. So that's it for example 4. Let's look at another one. Example 5 says each side of a square is increasing at a rate of 6 centimeters per second. At what rate is the area increasing when the area is 16 square centimeters? All right, so I've drawn my diagram here and I've labeled it with some changing quantities, and then I've defined my variables x to be the length of a side of the square and a to be the area of the square. So if I want to identify what type of question this is a square area question. And let's identify our goal as well. What are we trying to find? It says at what rate is the area increasing when the area is 16 square centimeters. So we're trying to find the rate at which the area is increasing over time, which is another way of saying dA dt. So if this is a square area question, then the equation we would use is A equals, the area of a square is its side length squared. And then from here, we'd like to take the derivative with respect to t on both sides and use implicit differentiation. If we do this, this is going to end up giving us dA dt is equal to 2x times dx dt. So at the moment that we snap our picture, we want to figure out what is the length of one of the sides and at what rate is the side length increasing. So it says when the area is 16 square centimeters. And so when the area is 16 square centimeters, so in this picture, the area is equal to 16 square centimeters, and the side length would be the square root of that. So in this exact moment in time where I've snapped my picture, the side length would be 4 centimeters. So we have dA dt is equal to 2 times 4 centimeters, and then we know that the side length of one of the square is increasing at a rate of 6 centimeters per second. So that's given right here, and now we can multiply, and doing so will give us that dA dt is equal to 48 centimeters squared per second. Let's write an interpretation of this. So when the area of the square is 16 centimeters squared, the area is increasing at a rate of 48 square centimeters per second. That concludes example 5. Let's move on to the next one. Example 6 says, a hot air balloon is rising at a constant speed of 5 feet per second. Guma is cycling along a straight road at a speed of 45 feet per second. When passing under the hot air balloon, the balloon is 30 feet above her. How fast is the distance between Guma and the hot air balloon increasing 3 seconds after she passes under the balloon? Round your answer to 4 decimal places. Let's go ahead and draw a picture of what's happening here. I'm actually going to end up drawing 2 diagrams. So my first diagram is here. Let's say this is Guma, and at the exact moment in time where she is passing underneath the hot air balloon is 30 feet above her. So let's say this is the hot air balloon, and this is directly underneath, and this is 30 feet. Okay, so what happens is 3 seconds later after she passes under the balloon. So 3 seconds later. Now what has happened is the hot air balloon has risen a bit. So here's the hot air balloon now. And Guma's traveling in this direction, and so she ends up maybe, let's say, here. And this was the point where they had kind of passed, or the Guma had passed under. So here's Guma on her bike. And so let me draw this down. And I didn't do a great job of doing that straight. So here, and then we have this, and then we have the distance between the hot air balloon and Guma. And if I did a decent job of drawing this, you should be able to tell that this is a right triangle. So hopefully you can tell that. My drawing's not the greatest. All right, so now let's go ahead and define some variables. And one last thing before I start to define my variables, I'm going to call this point here where Guma passed right under the hot air balloon, I'm going to call that point the origin. So it's a little bit easier when I come up with my definitions. So let's say x represents the distance between Guma and the origin. All right, so I've defined 3 variables. My y variable is the distance between the hot air balloon and the origin, and then my final variable c is the distance between the hot air balloon and Guma. So in my picture, this would represent x, this would represent y, and then the length of my hypotenuse in my right triangle here would be c. So let's go ahead and identify what type of question this would be. This would be a Pythagorean theorem question. And let's identify our goal. What is it that we are trying to find? It says, how fast is the distance between Guma and the hot air balloon increasing 3 seconds after she passes under the balloon? The distance between Guma and the hot air balloon is c, so the rate at which that is changing is dc over dt, which means that I'm going to take the derivative with respect to t. Let's go ahead and set up our relationship equation. I know that x squared plus y squared is equal to c squared, and I want to take the derivative of both sides with respect to t. And, we've done this several times now, so I'm going to just kind of quickly breeze through it. 2x times dx dt plus 2y times dy dt is equal to 2c times dc dt, and once again, I can divide my equation by 2 on both sides. And so we end up with this lovely equation here. And our goal is to find dc dt, which means every other unknown value we should be able to come up with. Okay, so now we need to figure out all of these unknown values. Let's start with x. I've frozen a picture in time, and I'm looking at this 3 seconds later. And so I want to figure out how far from the origin is Guma 3 seconds after she passes under the balloon, which 3 seconds after she passes under the balloon, this is where she passed under the balloon, so this is 3 seconds later. And if she's traveling a constant speed of 45 feet per second, then after 3 seconds, we could just multiply 45 times 3. So 45 feet per second times 3 seconds. The seconds would cancel out, and this would tell us that she traveled 135 feet in that 3-second time span. So that would be my x value at that frozen moment in time. Okay, let's figure out the y value. So the y value at the original starting time was 30 feet, but now 3 seconds have passed. And this is where students often get tripped up a little bit. The hot air balloon is rising at a constant speed of 5 feet per second. So the vertical distance, or the y value 3 seconds later, is not going to be 30 and it's not going to be 15. It started at 30 feet and then it would have risen 15 feet, so its new height would be 45 feet because I'm adding 30 plus 15, which is coming from the 3 seconds at a speed of 5 feet per second, means that the hot air balloon traveled 15 feet from where it started. So now the new height is 45 feet. And y, it represents the distance between the hot air balloon and the origin, but it's essentially the height off the ground. All right, so we said x was 135 feet, and dx dt would represent the speed at which Guma is traveling, which is 45 feet per second. And then y, we just said was 45 feet. And the rate at which the balloon is rising is 5 feet per second. And then c, once again, we will need to use the Pythagorean theorem to figure out what c is in that snapshot moment in time. So we have c squared is equal to 45 squared plus 135 squared. And we're going to end up with c is equal to the square root of 20,250 feet. So now in our equation, we want to go ahead and isolate dc dt. All right, so if we isolate dc dt by dividing both sides by the value we found for c, the feet are going to end up canceling out. And if we simplify this value, my numerator is going to come out to be 6,300 over the square root of 20,250. And then my remaining units we can see is feet per second. It does ask us to round our final answer to 4 decimal places. So this is approximately equal to 44.2719 feet per second. Let's write an interpretation of what our calculation means. So we have 3 seconds after Guma passes under the hot air balloon, the distance between Guma and the hot air balloon is increasing at a rate of 44.2719 feet per second. And that's it for example 6. Example 7 says an inverted conical water tank with a height of 12 feet and a radius of 6 feet is drained through a hole in the vertex. If the water drops at 1 foot per minute, at what rate is the water draining from the tank when the water depth is 6 feet? Round your final answer to 4 decimal places and don't forget units. All right, let's define some variables, because here we already have the picture drawn for us. And if you didn't know, conical just means cone or in the shape of a cone. And so this type of question is going to be related to a cone, and we want to find the rate at which the water is draining from the tank when the water depth is 6 feet. And so this is actually related to the volume of a cone. So if you don't remember the formula for a volume of a cone, we'll talk about it momentarily. But let's define some variables first. All right, so I've defined 3 variables: r to be the radius of the cone-shaped water, h to be the height of the water in the tank, and then v, the volume of the water. So if you don't remember the formula for the volume of the cone, we have that the volume of a cone is equal to pi over 3 times r squared, which is the radius, times the height. Let's identify what our goal is, what we're trying to find. So our goal is to find the rate at which the water is draining, and that's the volume of the water. So we have dv dt is what we are trying to solve for, which means that in our equation, we'd like to take the derivative of both sides with respect to t. Now, I'm going to go about this the wrong way to start off, because this is how students would normally do it. And then I'll talk about why we should probably try to approach it a different way. All right, so this is how we might go about it based off how we've done the previous questions. We've taken the derivative of both sides with respect to t, and we end up with dv dt is equal to pi over 3 times, and I need to use product rule, so we have r squared times dh dt plus h times 2r times dr dt. The reason that we probably don't want to go about the question this way is based off the given information. It says an inverted conical water tank with a height of 12 feet and a radius of 6 feet. If the water drops at 1 foot per minute, so let's identify what this is. If it's dropping, that means that this is dh dt. But you might notice that nowhere in the question does it tell us dr dt. And so I'm going to suggest that we go about this question a different way, because right now, the way that it's set up is we need a value for dr dt. So let's see if we can't go about this a different way. What I'd like to do is, in this equation, I'd like to eliminate r so that my volume formula is only a function of the variable h, so that when I take the derivative of it, I don't end up with dr dt in my formula. So here's what I'd like to do. We're going to use some geometry here, and I'm going to draw a two-dimensional right triangle, and this is going to represent half of my water tank. So my 2D picture here, this is my water tank, and then notice that if I draw the two-dimensional half version of the water, these are similar triangles because this angle right here is the same as this angle right here, and then they both have a right angle. That means that the third angle would have to be the same, and this means that these two triangles are similar triangles. And the reason that we care about similar triangles is because we can create a proportion between the side lengths of these triangles. And so these are not changing on the tank. The radius of the tank is 6 feet and the height is 12 feet. And so I know that we called our height of our water h and the radius of our water r. So we want to come up with a proportion or a relationship between these things, and the proportion that we can come up with is, in terms of the side lengths, is that h over 12 must equal r over 6. And what we can do now is, I said earlier that I'd like to try to eliminate the r variable, so I can solve this equation for r by multiplying both sides by 6. If we do that, we get r equals 6 times h over 12, which is the same thing as 1/2 h. So now we have this relationship, r equals h over 2, or 1/2 h, and now we can go back to our original equation and eliminate the r variable. So let's do that. So my new equation will become v equals pi over 3 times r squared, which I'm replacing or substituting r with h over 2, and then I'm multiplying this by h. And let's go ahead and square the fraction h over 2. That's going to give me pi over 3 times h squared, and then 2 squared is 4, and then we have times h. Now I can multiply the denominators. That's going to give me pi over 12, and then h squared times h is h cubed. So finally, we have v equals, or the volume equals, pi over 12 times h cubed. Now that our volume formula is only a function of the height, I can start to take the derivative with respect to t on both sides. And doing so I'll have dv dt equals, I can factor out the constant pi over 12, then I would use the power rule on h cubed, so I'd bring my power down, and then I'm using chain rule, so I'd need to multiply by dh dt. That's a lot easier to work with because this no longer has dr dt in it. I'm going to simplify my fraction. Pi over 12 times 3 is pi over 4, and then I have h squared times dh dt. We said earlier that our goal was to find dv dt, so I should be able to plug in all of my other unknown values. And so we have pi over 4. Our height, going back to the original question, said when the height of the water is 6 feet. So I have 6 feet quantity squared times dH dt. It says that the water drops at 1 foot per minute, so the height is changing, and it's because it's decreasing, I need it to be negative. So it'd be negative 1 foot per minute. If we simplify this, we get dV dt is equal to 6 squared is 36. 36 divided by 4 is 9, and so this is going to simplify to negative 9 pi cubic feet per minute, which we expected because this is volume, and volume is measured in cubic feet. So let's write a sentence to interpret our answer. When the height of the water is 6 feet in the tank, the water's volume in the tank is decreasing at a rate of 28.2743 cubic feet per minute. That concludes this video on related rates. Thanks so much for watching.